In this lecture, I discuss hypothesis confirmation. That is, ways how observing some evidence might justify increasing one's confidence in a hypothesis. Confirmation is an important part of the HD method. Confirmation is not based on deductively valid inference. In the HD method, we identify some C that is an implication of H. So H implies C, here symbolized by this arrow. Then, if H is true by modus ponens, we infer that C is true too. Furthermore, if we observe that C is false, then by modus tollens, H is false too. Popperian falsificationists put a lot of emphasis on modus tollens. There are some problems with that, as I've discussed in a previous lecture, but still, both of these inference rules are deductively valid. Unfortunately, however, these two rules don't tell us what to conclude if C is true. From the facts that H implies C and C is true, nothing of interest can be deduced about the truth of H. There is no valid deductive rule that can be used here. Instead, any such rule must amplify the information contained in the premises to infer the conclusions. We are making inductive inferences here, indicated by the double instead of a single line. Any inductive inference rule is fallible. This will not surprise you. I bet you all have made inductions that failed, be it when predicting the weather, self-diagnosing an illness, or investing in the stock market. The interesting thing, though, is that different inductive inferences seem to have different degrees of fallibility. Some make us quite confident that the hypothesis is true, while others less so. For example, you might hypothesize that of 10,000 baseballs, half have a cork center and the other half has a rubber core. If you selected 5,000 of these balls at random, opened them, observed their core, and found them to be half made of cork and half made of rubber, you would be pretty confident in your hypothesis, and rightly so. If instead you heard someone who had visited the factory report that she saw workers sewing baseballs both with cork and rubber centers, you probably would be a little more confident in your hypothesis, but not very much. But this example illustrates is that confirmation comes in different degrees. And the degree seems to depend on the kind and quality of the evidence as well as on the inference rule used. Such degrees of confirmation might be characterized qualitatively. The most recent assessment report of the International Panel on Climate Change, for example, offers 5 qualifiers for expressing confidence, ranging from very low to very high. Alternatively, people have attempted to quantify confidence. The most prominent route here is to use probabilities. That an observation O confirms hypothesis H then means that the probability of H given O is true is higher than the probability of H given that O is not true. This is, however, beset with a number of problems. First, not everybody agrees that it makes sense to assign probabilities to hypotheses because they interpret the concepts of probability differently. One prominent position, frequentism, interprets probabilities as the frequencies of repeatably observable events. Because hypotheses are not events, nor observable nor repeatable, frequentists argue that one cannot meaningfully assign probabilities to them. Another problem is that probabilities already are used to express a property different from confidence. I might say, for example, that the probability of tails when throwing this coin is 1/2. You might then ask how confident I am in this claim, and that is a separate question from the first one. Of course, one might answer the second question also with a probability, but then one must keep these two numbers clearly separate. The IPCC has chosen a different route. It qualifies uncertainty, that is, how likely something is, differently from confidence, as in this claim about climate warming. Understanding that confirmation comes in degrees helps understand the last step of the HD method. Observing C to be true increases our degree of confidence that H is true. But why? What makes it so that observing C increases our belief in the truth of H? The first answer is because H is compatible with C. When checking whether C was true or not, we could have made observations that contradicted H, thus leading to its rejection. But we didn't. Therefore, we are now more confident in H. This is a very weak justification of confirmation. First, one can deduce indefinitely many implications from a hypothesis, even though the truth of many of them seems highly irrelevant. Take, for example, the claim, "I have stomach cancer." One deductive consequence of such a claim is that indeed I have a stomach. But observing that I do have a stomach should not confirm the claim that I have stomach cancer. A proposed solution for this problem is to introduce some criterion of relevance for implications. Only the truth of relevant implications, in the stomach cancer case probably various effects of the cancer, would confirm the hypothesis. Specifying such a relevance condition, however, is tricky and requires a lot of background knowledge. An additional problem for the compatibility argument is that very many hypotheses are compatible with any given observation. This is called the problem of underdetermination. Take, for example, these three observations marked here by red dots in a two-dimensional graph. This curve, described as hypothesis 1, is compatible with these observations. Does that mean that the observations, confirm this hypothesis? Well, here's another hypothesis that is also compatible with the observations. And so are indefinitely many other ones. Each of them are substantially different hypotheses, compatible with the three observations, but making different claims about the world otherwise. A possible solution to this problem is to select the simplest hypothesis compatible with the observations. For the curve-fitting case, this might work, as one might be able to rank these different curve hypotheses according to their degree of polynomial. But in many other underdetermination cases, such a simplicity ranking is not available. Take, for example, the hypothesis I have stomach cancer again. Theory indicates that one relevant consequence of stomach cancer is heartburn. So when I experience heartburn, should I substantially increase my confidence that I have stomach cancer? The answer is no. Very many hypotheses are compatible with heartburn, so it is not a very strong sign of stomach cancer. This example shows that the compatibility of hypothesis with observation is not a sufficient basis for a confirmation. We need something stronger than that. One proposal is that C confirms H because C would have been very unlikely if H had been false. That is, the possibility to observe C would have been remote if H were false and some other hypothesis true. If we know that there is such a relationship between C and H, then we can safely rule out those alternative hypotheses compatible with C. The philosopher Deborah Mayo calls a hypothesis test that satisfies this condition a severe test. Severe testing solves our heartburn problem. Although stomach cancer is compatible with heartburn, the chance of suffering from heartburn if one has stomach cancer isn't higher than the chance of suffering from heartburn if one has reflux disease or some other gastrointestinal disorder. Testing the cancer hypothesis with observing heartburn thus is not a severe test, and observing heartburn does not substantially confirm the cancer hypothesis. Severe testing, however, requires a lot of information, in particular about alternative hypotheses and the probability of making the observation one made if those alternatives were true or false. Furthermore, this proposal does not solve all problems of confirmation either. What, for example, if one first made an observation and then constructed one's hypothesis in such a way that it would imply this observation? Such a hypothesis might meet the severe test condition, but arguably such an observation would not confirm the hypothesis. Take curve fitting again. It seems illegitimate to construct the curve in such a way that it fits all the available information, then claim the curve as one's hypothesis, and then use the same data points as confirming evidence for one's hypothesis. Instead, only observations that have not already been built into the construction of the curve should be used in confirming it. Finally, consider this case, where severity seems insufficient to justify strong confirmation. The police use new breathalyzers, which falsely display drunkenness in 5% of the cases in which the driver is sober. However, the breathalyzers never fail to detect a truly drunk person, and 0.1% of the population is driving drunk. Suppose a police officer now stops a driver at random and forces the driver to take a breathalyzer test. It indicates that the driver is drunk. How confident should the officer be that the driver is actually drunk? Please pause the video and write down your answer before continuing. The correct answer is the probability that the stopped driver is actually drunk is about 2%. I suspect that at least some of you got this wrong. Why? Because although this case meets the condition of a severe test, it does not confirm the hypothesis strongly. Let's see how this works. The hypothesis here is that the driver is drunk. The indication of the breathalyzer is a severe test. It indicates with 100% chance if the hypothesis is true, and only with 5% chance if the hypothesis falls. Yet, because the base rate of drunken driving is so low in the population, the relative small error of wrongly indicating, even though the hypothesis falls, becomes very influential. Consider this case, where we have a sample of 1,000 drivers shown as these little gray boxes. Only one of these 1,000 is driving drunk, and the breathalyzer correctly identifies him or her here in blue. But the breathalyzer also falsely identifies 50 out of these 1,000 as drunk, although they're sober, indicated here in red. Altogether, the test identifies 51 people as drunk, of which only one is actually drunk. 1 out of 51 equals roughly 2%. Thus, the probability of someone identified by a breathalyzer to be actually drunk is about 2%. The breathalyzer indicating thus does confirm the hypothesis that the tested person is drunk, just not as much as you probably thought. Because the initial confidence in the hypothesis was so low, even such a severe test could not increase the confidence very much. In order to deal with such cases, we need a Bayesian approach to hypothesis testing. I will discuss such approaches later in the statistics lecture. To conclude, confirmation of a hypothesis by an observation comes in degrees. But to simply note that the hypothesis is compatible with the observation is not enough. Instead, we also need to ensure that the hypothesis made the observation very likely, and that the observation would not be very likely if the hypothesis had been false. Such a severe test condition improves the quality of inductive inferences substantially, but even it faces a number of problems.